Well, welcome back, and I do hope you and your family are keeping well. So what we're going to do today is the sort of first introductory lesson to A-level. And I'm reminded of a story, as I always am with my teaching. A friend of mine who I used to teach with interviewed a lot of physicists and said, what do you do? And when it came round to it, basically the main thing they were actually doing was making measurements. So the first thing we're going to look at is how we make measurements in physics and what units we do those measurements in. It's interesting because if we look at, say, a measurement of my laboratory, okay, so my lab, and if I measure the sort of width of the laboratory, it's 10. And I hope you immediately don't jump to any conclusion about what that 10 means, because it's really, really unhelpful. Because the measurement of the width of my laboratory has a unit with it as well. Obviously, it's a length. And so what I'm really saying is it 10 meters? Is it 10 feet? Is it 10 inches? Is it 10 millimeters? Is it 10 furlongs? Is it 10, to remember now, fathoms for depth? It's really important that if we have a quantity like 10, we also have a suitable unit after it. And the textbook mentions the fact that it's not just good enough to have a quantity and a unit. We've got to all agree on what units we're using. They give the example of the Mars Climate Orbiter, which was well over $100 million to make. And it crashed because the NASA scientists in America were working in pounds and feet and inches, and the scientists in Europe were working in sort of meters and kilograms, and confusing those units, as here, confusing the units for the width of my laboratory would, in the case of the lab, probably mean you didn't buy enough floor covering or something, or you bought far too much. What if you imagined it was miles? But in the case of the Mars Climate Orbiter, it was destroyed. The systems couldn't work thinking that everything was measured in the same units. Now, we've got a quantity here, okay? So you know that this number here is an amount of something, okay? And typically, quantities have units. I'm going to choose meters today, the unit of length that we agree upon. Now, quantities don't have to have units, so I can think of efficiency, which is just quoted as an amount up to 1, so 0.8 efficient, or as a percentage, because those are ratios. Now, the crucial thing there is that you've got an example of a quantity that doesn't have units. And if you divide one unit by the same unit, if you measure your efficiency in joules divided by joules, or watts divided by watts, or whatever, you'll lose the unit. And never mind what units you work in, as long as the top one and the bottom one in your maths is the same, you'll end up with the same answer as everyone else, okay? A quantity that doesn't have units. We could describe it as being dimensionless, and we'll come to that later on. Okay, so I want to talk to you now about what units are we going to choose. Do you want to work in Fahrenheit, feet, pounds and inches, or do you want to work in a system that is agreed across the world by most countries that makes the maths a lot much easier? So I'm now going to look at an idea I find quite difficult to explain. We're going to look at the way we measure things in physics, and the idea of a base quantity, a property that we can measure of something that cannot be measured using any other methods, any other units. Okay, it's kind of the most basic way we can measure something. And that'll make more sense in a minute. Okay. What unit that is in, and we're going to use the System International, so we're going to use the one that most of the world agrees to use. Okay, and what the symbol is we use for that unit. And then the last column on this table I'm going to reveal is what we call the dimension, and it allows us to do something called dimensional analysis, which is not really in at A-level exactly, but it's a really interesting idea, an interesting concept that I think will help you. Okay, so if that's a mystery, this won't be. There are 7 of these, okay, and there is no other way, more simple way, to get the length of an object. The length is a base quantity. Now, what I mean by that is, that isn't true of area, okay? Area, is in meters squared in the System International, in SI units, and that can be broken down into a length multiplied by a length. So length is more basic, okay? We know its unit that we're going to use, the base unit, is the meter. We know the symbol is a little m, and that's really important. And we use the letter L to denote length in terms of dimensions. And I put this bit in blue because it's not really all that important for A-level, but you will find it very useful. Now, there are 7 of these, so I'll whiz through them. Mass, okay? In the SI system, okay, mass, given the little letter M to abbreviate the word mass, okay? It's measured in kilograms, okay? Now, that's really confusing because we seem to have a prefix here of kilo, but I'd like you to think of the base unit as being one of them, 1 kilogram. There's the unit symbol that you know, the kilogram, and be very careful, that's a small k and a small g, and we're measuring the dimension of mass of something, okay? Time. You can't break down time into something simpler. It's not kind of lengths and things multiplied together, okay? So whenever we write the word time, we can use little t. We're going to measure in seconds. Can I say that again? Seconds, because at A-level we'll have hours and minutes and years, but we must measure in seconds, must calculate in seconds, yeah? Little s, be very careful with that one, and I have to be, because if you write a number in front of it, it often looks like a 5, okay? But it's a little s, and it has dimensions of time. Electrical current, yeah? The ampere, okay? Named after the guy who did the work. Now, you might remember from GCSE, and it's a bit annoying, that amps in the electrical current in equations is abbreviated to I. I always call that the intensity of flow. Okay, it's the ampere. Have I spelled that correctly? Don't know. Symbol capital A. Okay, and the dimension I. Okay, and there's an interesting point here. Okay, that if the base unit is named after someone, which the ampere is, the base unit has a small a. Okay. But the unit symbol, because it's named after someone, has a capital letter. Okay, and you'll see that coming up quite a bit. So I told you there were 7 of these, 6 needed for A-level. Okay, now here's a bit of an annoying one: the amount of substance. Count up the number of things. Okay, given the symbol little n. Now this is really confusing because I have seen the amount of substance, the mole, be a capital N in equations. So when you do this mathematically, check your equation to see what the letter in the equation represents. Is it the number of moles, okay, which is usually a small number, or is it the number of particles, which is usually a very large number? And you've got to be really careful there. Okay, unit symbol, the mole, and in dimension N, I suppose, for number of. Temperature, okay. This is one we'll deal with much later on at A-level, and it's really important. Okay, you can't measure temperature in terms of other things. Okay, so it's a base quantity. The unit is the Kelvin, small k. Okay, because it's the name of the unit. The unit symbol is the Kelvin, capital K. Okay, so it's not degrees C and it's not Fahrenheit, and there's a good reason for that. I'll give you a good reason, okay? You've got 0 degrees C. What happens if you double the temperature? you're still at 0 degrees C. It doesn't kind of make sense, okay? So we use the absolute temperature scale, named after Lord Kelvin, okay? And I won't tell you, but some of you might be interested to find out why was Lord Kelvin called Kelvin, because it wasn't his real name, okay? It's quite interesting. It took me a while to work that little puzzle out. It has this really weird symbol, again, which you won't typically use, but I'd like to show you, okay? And that's it for A-level, okay? But we've got to do things properly, so here's the last one. Yep. How bright something is can't be measured in other terms, okay? Can't be measured in meters or amps or what have you. So that's luminous intensity. We give that the letter L, capital L. It's measured in candela, which I think is really cool. It's kind of like how many candles would represent that brightness. Okay, the candela has the units CD. Okay, a little bit confusing. The C there looks like a prefix, but it isn't. And even more confusing, in the dimensional analysis, which I'll show you, it has the letter J. Okay, not in any way to be confused with joules or anything like that. So there are our 7 base quantities. Okay, so this isn't quite true, but I tell students to give them an idea that if you had a meter ruler, some scales, a stopwatch, an ammeter, something to count, a thermometer and a brightness measurer, you could measure every quantity in the universe, okay? I mentioned earlier on that if you wanted to measure the area of the floor of my lab, you just needed a meter ruler, okay? If you want to measure, say, temperature, it's pretty clear that you just need a thermometer. So it's difficult to explain what I mean by base quantities, but it sort of kind of almost suggests in your brain that there are sort of 7 instruments that you would need, and if you had those 7 instruments, you could use them in clever ways to measure other things. Let me give you one more hint on that. Acceleration's not on there, okay? But you can measure acceleration if you've got these, because you remember it's meters per second. So you need some measurement of length and some measurement of time. Yeah, you use the base quantities. So at A-level there are 6 of them. Ignore the candela, okay? And we don't do true dimensional analysis at A-level, but I'm going to show you that, I think, because it's really important, okay? You know what the units are now, and this is a table to know, yeah? You need to know these sorts of things. So what I want to do now is take this a little bit further and see if we can use these base quantities to produce some other units. And I hinted at things like area and acceleration. So we've got our base quantities and our base units. Now let's put some of those units together and do some derived units. Okay, so I've already hinted at area is a derived unit without any kind of special name. It's just area measured in meters by meters, so meters squared. But I'd like to look at a couple more examples that mix together base units. Okay, so for example, let's have a look at speed. Well, you know that speed is distance travelled over time taken. So I will just write speed as d over t. Okay, I'm not going sort of into real detail here. I'm just making some simple points. Okay, now we know the units of this one is meters, and we know the units of that one is seconds. So that gives us meters per second, or perhaps another way of writing it is meters per second. Okay, so that's simple GCSE, but you can see speed has a derived unit taking 2 base units and dividing one by the other and saying that speed is measured in meters per second. It doesn't have a name, okay? It's not named after a famous physicist, or it's not called FJs or something like that. It's just meters per second. But I just want to pause for a little moment here and say this isn't really good enough for A-level, okay? This is meters divided by seconds, okay? And this is the same as meters times by 1 over seconds, okay? So this is the same as meters multiplied by 1 over seconds, okay? And 1 over seconds is the same as seconds to the minus 1. So this is the same as meters multiplied by seconds to the minus 1. So there we go, okay? From now on at A-level, we're not going to use this sort of slash notation, okay? We're going to use sort of powers above, and in the case of speed or velocity, yeah, it will be measured in meters per second. That's what we say, but we write meters seconds to the minus 1. Okay, so obviously if we have acceleration, so let's have acceleration. Okay, acceleration, if you remember, has got units of meters per second because it's the change in speed over the time change, the time taken. Okay, so that's quite awkward because it's sort of meters per second divided by seconds, but I don't like that at all. Okay, it doesn't make sense. What you learnt at GCSE was it was meters per second, so meters per second squared, and I think you're ahead of me on this one. At A-level, this is not good enough, so we're going to write meters seconds to the minus 2. So we've got some derived units there, yeah, the derived units, and we've written the derived units in the correct way for A-level. Okay, and finally, these guys don't have specific names. Okay, they're not named, these units, derived units, are not named after particular scientists. So let's now look at some derived units with special names. Okay, so the one that we always pick to teach is force. And I'll show you why force has got a special name to it. Because what are the units of force? And to work them out, a good way to do it is to get an equation that's fairly easy to work with. So F equals ma, okay, makes the point that bring your GCSE to A-level. It's really important you remember GCSE formula and can use them because it's a very important formula. Capital F, yeah, the force is equal to the mass times by the acceleration. So if you look at this, it gives you the units for force. Yeah, the units of force are mass times acceleration. So they're kilogram meters per second squared. Okay. Now, you might think, what? That's not what we learnt at GCSE. Well, we're not even going to use this at A-level. Okay. To say that, you know, you take a kilogram mass and you put it in the Earth's gravitational field and it feels 10 or 9.81 kilogram meters per second squared is just madness. To say that a car, when it's driving away, has a force of the engine equal to 2,000 kilogram meters per second squared, that's madness. Okay, so we're going to name this one, we're going to give it a name, and we're going to call it the Newton. Clearly after Isaac Newton, and he wouldn't have known this, of course, okay, but it's been decided to name the kilogram meters per second squared after Mr. Newton with a small n, okay? But the unit now, all of that lot, is going to turn into the Newton. Now, no one has ever asked me this at GCSE, but whenever we write the letter n at the end of a quantity, like 10 newtons, that n actually represents these base units, okay? It's sort of those hidden in there. So we've taken a complicated multiplication of base units and we said, let's get rid of the complication. let's just give that lot a name. Okay, now you can think of probably many other ones. Okay, a common one is pressure. And pressure, if you remember, the pressure is the force divided by the area. Okay, and if you do it in SI units, okay, well, crumbs, force we've just worked out is kilogram meters per second squared. Okay, area is meters squared, but it's divided by area, so it's meters to the minus 2. Okay, you'll notice that meters crop up here and there. Okay, so let's get rid of that one and one of those. So we now have kilogram seconds to the minus 2, meters to the minus 1. Do hope I've got that right. And the whole point is it's getting really fiddly now. But because we're in SI units, pascals, job done. Okay, we will name that lot after a guy who did a lot of work on pressure, so we can get rid of that problem and just have the special name for this lot, just call it a pascal. And there are another, I think, 20 of these in the SI system, and you'll come across them, but you won't need to go into them in too much detail. But do be aware that embedded in these units is some more complicated stuff relating to the base units. So we looked at derived units and the ones, or some of the ones that are named after people. Maybe you had a bit of a block on that, or maybe you went, yeah, there are loads of them. What about joules? What about volts? What about coulombs? The list goes on and on and on. Well, it goes on for another 20 of them. Okay, so that's going to be a really useful way of naming complicated collections of base units. Now, back to base units, and I'm going to introduce the idea of dimensions as well, just to help you a little bit. This comes up a little bit in A-level. Testing formula. Okay, so I'm going to start off with a really stupid example. Is this formula correct? So, is the distance equal to a certain length, for example? Okay, now, you might think, well, what am I doing here? It's a kind of silly way of describing what I want to show you. I want to check whether this side of the equation has the same units as that side. And I mean base units. Okay. So, this one, yeah. If it's a distance, we measure distance in length or meters. So that's going to be in meters. And if it's a length in the SI system, we measure it in meters. So in terms of what we measure, this side is measured in the same units as that side. You might think, what? This is mad, okay? No, it's really important, okay? Because it means that this formula is dimensionally correct, okay? It uses the same base units on either side. Okay. Now, in terms of dimensions, okay, which is not really an A-level thing, distance is a measurement of length. Length is clearly a measure of length. So the dimensions on this side are the same as on that side. So this formula is dimensionally consistent. It really could be true. Now, where it can be wrong, of course, it's still dimensionally consistent, is what the numbers are in front of these. So you could say a distance here is equal to a length there, and you could make it in the same units, but you could say 10 meters equals 12 meters, which is utter rubbish. Okay, where the quantities are wrong. Okay, or you could do something like the distance to the moon is 6 meters from Earth. Yeah. Now, clearly that's rubbish because the quantities are wrong, but it is correct to state that a distance to the moon is a measurement of length. So that formula is dimensionally correct. So what I'm going to do is look at some other formulae and we're going to check whether they're dimensionally correct or not. So let's do another example, and I'm going to pick one that you won't have come across yet. So here we go. So the formula we're going to look at is this one. N lambda equals d sine theta. Okay. This is a formula from optics, in fact, or at least from waves, which is really interesting. Okay. Now, I've kind of spoilt it, haven't I? Because I've told you it is a formula. But let's just check whether it's dimensionally correct, whether it's consistent. Okay. So the first thing to do is for me to tell you what these are. That's n, number of, just number of. Okay, 1, 2, 3, 4, 5. So you'll agree that that doesn't have any units. So we can ignore that. Okay, it's dimensionless. It has no units. Lambda, come on, GCSE. Yep, lambda. Wavelength. Okay, and wavelength must be measured in meters. Okay, d sine theta. Well, d is a distance, so that's measured in meters. Okay, and an angle doesn't have any units after it. It's not in, it doesn't have any base units or even a named derived unit. Okay, so sine theta is just a number on your calculator. Okay, it's a dimensionless number. Okay, so no dimensions there. So meters on this side, meters on that side. I prefer to do it in terms of dimensions. Length on this side. Perhaps I should have done that in purple. Length on this side and length on that side. So this formula is dimensionally consistent. It may be missing a constant, which it isn't, okay, but it is a measurement of length on this side must be equal to a measurement of length on that side. Okay, so we've checked that this formula is dimensionally consistent. So I'd like to just do one more to give you another example of this. So I'd like to do one more example to show you how powerful this technique of analysing formula using base units or using dimension analysis is at A level. Okay, so here's another example. So I'm going to propose this formula, F equals mv upon r. Okay, and I'm suggesting that this formula tells you the force that you need to pull something around when you swing round in a circle. Okay, it's the centripetal force. It's the force holding the moon in as it goes around the Earth. Now, don't say anything if you feel awkward about this. Look at it in another way. FJ has invented this formula. Okay, let's test it to see if it is a real formula or at least if it's dimensionally consistent. So if this side of the formula is measured in units of force, that's newtons, then that lot must be measured in newtons. And if it's not, the formula is rubbish. And if it is, the formula is dimensionally correct. It may not tell you something useful, but it does mean the units on this side are the same as on that side. So it's not like saying that a length equals an area, which would be completely useless because there would be different units on either side of the formula. Okay, so let's tease this apart. Right, so we remember that F is also the same as ma. So that bit is the same as ma, mass times acceleration. Okay, and we've done this before. Mass, yeah, so we've got kilograms and we've got acceleration, meters per second. Okay, so let's see what's on this side of the formula. Okay, so on this side, I'll come down here, we've got mass, which is kilograms. Yep, we've got velocity, which is meters per second. Okay. And then r is a radius, yeah? So r is a distance, if that makes sense, okay? Just a measurement of length. And it's over r, so it's r to the minus 1. So we've got to multiply this lot by meters to the minus 1. So you'll notice that that goes and that goes. Okay, so I'll put a circle around that lot and a circle around, well, I will rewrite it as kilogram seconds to the minus 1. Okay, and you'll immediately notice that kilogram meters per second squared is not equal to kilogram seconds to the minus 1. So this formula is complete and utter rubbish. Okay, it cannot work. It can't work even if you put a number in there, a constant. Okay, if you put the number 10 in there, it still doesn't work. It would work if you put a constant in that had dimensions. Okay, so this formula is complete and utter rubbish. Okay, now it might be a little interesting challenge for you to work out what's actually missing. Well, let's do that very quickly. We're missing a meters and we're missing a per second. So we're missing a meters seconds to the minus 1. Meters seconds to the minus 1. We're missing velocity, yeah, meters per second. So this formula really should be written, yeah, kilogram meters per second squared on this side, kilogram meters per second squared on this side. It's missing a velocity, so there's another v in here. So the correct formula for centripetal force is F equals mv squared upon r. And I purposefully wrote this incorrectly to check whether it was dimensionally consistent, or at least using base units. And that's exactly the sort of thing you might be asked to do at A-level. Now, just before I finish on this, I have to do this in terms of dimensions. Dimensions don't come up at A-level, but real scientists find them, really, really useful. Okay, so we've got here mass, kilograms, length, and we've got time to the minus 2. Okay, and every physicist in the world knows that force is mLT to the minus 2 in any units. That's the crucial thing, yeah? You can get a force by multiplying a mass by a length and dividing by a time squared. Okay, it might not be in SI units, it could be in any units, but force in any language, any units, must have dimensions of mLT to the minus 2. Okay, and we saw that this side was mass time to the minus 1. Okay, so the dimensions of this side are not the same as this side, so that formula is dimensionally inconsistent. It can't exist. This is not in dimensions of mLT to the minus 2, and therefore that is not a measurement of force. And in SI units, this side is not in kilogram meters seconds to the minus 2, so mv upon r is not a measurement of force in newtons. So I hope you've got a good understanding now of measurements in physics, the SI unit system and why it's important to work in SI units now, and particularly to always work in units that are agreed. So if you're going to measure length, measure it in meters. If you're going to measure time, measure it in seconds. And of course the A-level, we'll put it in kilometers, we'll put it in hours and years and things like that, and you've got to make sure you're measuring in the right unit. We also looked at how you could check a formula had the same units on either side. So what were the base units of the formula? And that comes up quite a lot. And then I added a bit that's not quite in the A-level, but we checked whether formula were dimensionally consistent, which is kind of the same sort of thing. Okay. Anyway, I do hope you found that lesson useful. I'll be making some more soon, and I look forward to seeing you then.